move to the next participant. Let me present the Richard Wagner will show us his HL-20 NASA simulator. Richard, are you ready?
I am. Thanks, Peter. And I like your poster. That was very nice.
Thank you. The mic is yours. The presentation is yours. Go ahead.
Okay. Well, thanks for inviting me to the meeting. It's nice to see some old friends. Brad and I have known each other since about 1990. I first saw him when he was doing a presentation at the Rochester Fourth Conference, and he blew me away. He was doing a presentation on a backward chaining inference engine that he was working on for his PhD. I don't know if I know the rest of you, so it's nice to meet some new friends. Good morning from Colorado, and I think for a lot of you, it's actually good afternoon, right? So why don't I start out? Let me share my screen with all of you. Figure out which one to share. Just a moment. Okay, let's try this. Okay, hopefully you can all see my presentation here. I'm going to work with this for a short time, and then we'll get into some code, which I'm sure you guys are mostly interested in. But as Peter said, I'm going to show you some of the work that I'm working on right now on my own. Why don't I begin by doing a quick introduction so you can see just who this guy is, because none of you really know me. I'm an aerospace engineer. I got about 40 years of experience in the industry. Got my BS at Penn State University and my master's at Colorado State. I've been using Forth professionally since 1989. Began using it when I was working for the US Navy. I've worked with Polyforth, CM-Forth, LMI-Forth, ProForth for Windows, VFX, SwiftForth, probably a few others that I don't quite remember. But I worked with a lot of different Forths over my career. Used to be a member of the Forth Interest Group when it still existed. I presented papers at both the Rochester and Formal conferences, and I was the director and chairman of the 2000 Formal Conference in Monterey. Unfortunately, that was the last conference we had before FIG dissolved. There's my email, if any of you would like to write, and I have a website. You can see it there, radicalnovelties.com. The other thing I thought I'd do is show you a few of the projects that I've worked on over my career, because I've used Forth in some cases as the main maker of the product, and in other cases as support in a background role. The picture you see right here is me in the Stratolaunch simulator. I was the head of simulation, flight simulation at Stratolaunch, and this is me sitting at the operator's console of the simulator. Our two pilots are up in the pilot seats. I don't know if you guys will be able to see my pointer here, my cursor here, if I should switch over to the laser pointer thingy. Let me see.
Yes, we can see that.
Can you see it? Okay. All right. Right behind me here is another console. This is the flight engineer's console. His seat's right here. There's nobody there. Right after I took this picture, I quick slipped over there and acted as the flight engineer for our pilots. But we use this simulator for training our pilots and for engineering studies, and also as a marketing device, because we couldn't fly the airplane too often. So when people came to visit, we showed them a sim. You'll see more of it in a minute. So here are some of the projects that I've worked on, kind of in a chronological order. For the US Navy, I did a ton of different work there. All the different programs that I worked on, none of them had closed form solutions. So it required using a computer to find the answers. And I did a ton of work in Fortran, did a bunch of work in C, and then finally I joined a group that started this project right here, the sensor-driven airborne replanner. This is an AI-driven UAV control system. It ran on the RTX 2000 here, and this is where I learned Forth. I taught myself Forth to work on this program, and it was a revelation to me because suddenly whatever was in my head was coming out through my fingers, and I was seeing it operate in front of me. And I have never experienced that with any other programming language. This project was done completely in Forth. We had a flight simulation that I wrote in Forth, and then the airborne system was also done in CM Forth that ran on the RTX 2000. So I worked at MCI, the telephone company. They had something called the site control computer, which was based at every network node around the world and allowed them to communicate with all of the different hardware in that room. It's a very important computer system, mission critical. And that was all done in LMI Forth. Worked very nicely. They tried to rewrite that later in C++ and failed. At ITD Corporation, which some of you may have heard of, worked there with Chuck Moore, John Reibel, Skip Carter, Jeff Fox, and a few others. We developed a TV set-top internet appliance driven by the i21 processor. Jeff and I wrote the Forth for it. He began the assembler work, and I picked it up and ran with it from there. We did some nice work there. It just didn't happen to work out. At CAFnet with Skip Carter, who's a Forther, Skip and I developed a native WML browser that ran on handheld devices at the time. That was actually a big deal. Nobody else had that working. Later on, I moved to Maston Space Systems, and you can see what we developed there was vertical takeoff, vertical landing, suborbital rockets, essentially sounding rockets. The difference being from a normal sounding rocket that after this one goes up and does its work, carries your instrument package up, it brings it back to you, where other sounding rockets drop it in the ocean. So all of the work they did there was in MATLAB and Simulink. Very, very bad MATLAB and Simulink. So bad that the original author couldn't get it to work himself anymore. And that's when they called me in. And I couldn't get it to work either. So I used VFX Forth in a background role there to do different studies, look at different systems and stuff like that. Later on, Analytical Methods, which was a wonderful company to work for while it lasted. We developed a backpack portable UAV. This is a picture of it over here. I wrote the flight simulation for that UAV, and then that was in Forth. And then we developed the STANAG 4586 control system. That was in C. Beautiful project that we worked on there. And then, like I showed you before, here's Scale Composites. This is the big airplane. We called this airplane ROC, R-O-C, which was the giant bird that could lift elephants in mythology. Originally, I worked for Scale Composites. This was our contract there. And I was made the head of the flight simulation. And then after Paul Allen died, Stratolaunch reformed and stole all of us from Scale Composites, and I was still the head of flight simulation. So again, this is also, they wrote this flight simulator in MATLAB and Simulink using fresh out people that didn't know how to do it. And they created quite a mess. A great deal of the internals of that simulator didn't actually work. And then there were things where you could throw a switch and it would hang. So I finally convinced them to let me rewrite it. And I rewrote it with, I don't know how many of you know Rick Van Norman. He's the author of Swiftforth. I hired him, and he and I worked on it together and brought up a simulation in a matter of about 2 months. Really nice work. Later on, at Scale Composites, I worked on a system called Nimble Dragon, which was a flying wing UAV. And I wrote the simulation and control system for that. Unfortunately, they forced me to do it MATLAB and Simulink. But I used VFX Forth to do a lot of the research in the background on that. Big supporting role in that program. At Kratos, we developed unmanned aerial systems, mostly as aerial targets. Low-cost airplanes, this is a jet, that can be shot down. This airplane right here costs about $500,000 a copy, which the military thinks is pretty cheap. The flight simulation that they wrote is the nicest Simulink I have ever seen. They know what they were doing. So they wrote the flight simulation in Simulink. The flight control system that went on this airplane, this one's called the BQM-177, is hands down the worst C I have ever worked on in my life. I don't think I can bring it up very quickly, but the system took up about 15 megabytes of source code. It was written by people who didn't know what they were doing in the beginning, and then they never fixed it. They just kept building on top of it. One file that I was working in, I actually printed it out. It was 60 feet long and 8-point font. Imagine trying to find the needle in that haystack. So again, I used VFX in a supporting role in that program. Oh, by the way, they brought in 6 other consultants before they brought in me. And they all worked on the system for a while and then threw their hands up and said, that's enough, I'm leaving. Somehow I was able to make progress with it. I don't know how. And then finally, I think this is one of the last ones I've got here, is Sea Aerospace. I just finished up a program for Sea Aerospace. They needed independent verification that their control system works. So I wrote a simulation of Dream Chaser in Forth. We connected it to their control system, which was written by Draper Labs and MATLAB and Simulink. And then we allowed the control system to fly the simulation. And we were able to show that it actually does work. So that was pretty cool. I think we helped NASA with get some confidence in what they had written there. And by the way, I don't know how many of you are familiar with Draper Labs. It's a big name. You know, if it wasn't for Draper Labs, we wouldn't have reached the moon. I was expecting to see some of the most beautiful code I'd ever seen in my life. Wasn't the case. Their code was quite pedestrian. I was just kind of surprised by that. So, finally, this is some other work I've done. I've done quite a bit of computational fluid dynamics in Forth. You can see some results up here. The left-hand figure here is a rectangular grid wrapped around an airfoil. That's a 4th generated grid. In the center here, this is a simulation of Mach 4 flow over a 15-degree wedge. The dark line that you see here is a shock wave, okay, which is what we would expect to see. And then, I don't know if you can see it on your computers, but there's thin dark lines that are back here behind the first shock wave. Those are called Mach waves. And the fact that the CFD simulation produces those shows that it's working really nicely. On the right figure here, this is from my engine simulation work. This is a collector. There are exhaust pipes coming together from the top and from the left here. The cylinder at the left is not exhausting at the moment. Its valves are closed. The cylinder at the top is exhausting. And the exhaust pipe going out to the atmosphere is on the right. You can see the velocity vectors showing the direction of the gas flow. And what surprised me was there's actually a vortex formed over here on the left. Whoops, sorry. There you go. A vortex over here on the left. And that's not what I expected. It's a really nice result. I went back to grad school a few years ago and continued my engine performance, engine modeling in CFD. And you can see some of those results from it here. I actually created a simulation that can model an engine and predict its power and torque curves. So that's what you see down here. Again, that was all done in Forth. So let's talk about my current work. Right now, I'm developing a flight simulation and a control system for the HL-20. I'll show you a picture of that in a moment. The reason that I wanted to do this was I wanted to develop some on-orbit control algorithms that I don't have in my pocket for rendezvous and proximity operations, RPO. I wanted to develop atmospheric algorithms that could fly the vehicle back from reentry to a runway landing. I'd like to have them in my pocket too. I wanted to develop the embedded control algorithms in an AI-driven control system like we used for the STAR project that I showed you for the Navy. And then finally, this is probably actually the biggest driver. I wanted to have a control system in my pocket ready so that I can show customers this thing and convince them to do things my way rather than using MATLAB Simulink and screwing it all up like they're doing these days. Okay, so that's the reason that I wanted to do this. So here's HL-20. NASA called this the personnel launch vehicle. The idea behind it was to carry astronauts from Earth up to the International Space Station and return them with a reusable vehicle. Not just a reusable vehicle, but one that can alter its flight path coming back from reentry so it can land wherever it needs to. With a return capsule like we typically use these days, they can actually alter their flight path a little bit, but not dramatically. So they're almost 100% driven by gravity. Whereas the HL-20, because it can actually generate lift and direct that lift, it can make turns. So it can turn off of its current path, and if there's a runway over there to the right that it can actually land on, it can go over there if things go wrong. You can see it's sorry, I didn't include the metric measurements here, the SI measurements, because for some reason these days, even now, aircraft stuff is all done in feet. But it's 28.25 feet long, only about 14 feet wide, weighs 19,000 pounds. If I remember right, it carries 6 astronauts altogether. It's called a lifting body, okay? And that's because it doesn't really have wings. You can see it's got these fins right here on the left and right. They generate a little bit of lift, but not much. The body itself is what generates almost all of the lift. And it's not a lot of lift. So this thing, while it does fly, it still descends a little bit slower than a brick. Okay, so for instance, from about 10,000 feet, you've got about 1 minute until you're on the ground. So it comes down rather quickly. Okay, so I want to show you a little bit about what it takes to simulate something like this. When we talk about simulating a vehicle, one of the first things that we have to do is figure out what axis systems we're going to work with. Okay, this is what we typically start with. This is called a body fixed axis system. You can see how it's attached to the HL-20 here. Typically, it's centered at the vehicle's center of gravity. The x-axis, the x-axis points out the nose. The y-axis points out the right wing. The z-axis points down out of the belly. Okay, and the axis system is essentially attached to the vehicle. If the vehicle rotates, the axes rotate with it. If it translates, they translate with it. They're always on the vehicle. And then what we do then is, you can see this arrow P here is the roll rate. Okay, the angular velocity of the vehicle about its x-axis. Over here you can see Q. That's the angular velocity about the y-axis. In other words, the pitch rate. Z here, R here is the angular velocity about the z-axis, so yaw rate. And I forgot to say that P represents roll rate then. Okay. What you don't see here, there are also velocities. Picture that the vehicle is moving along its x-axis through space. The velocity along that x-axis through space is called U. Along the y-axis is called V. And along the z-axis is called W. Okay, so X, Y, Z, PQR, UVW. All right, that's kind of how it works. Now, every dynamic simulation is driven by, at its core, a set of governing equations. Okay, in computational fluid dynamics, those equations are the governing equations of fluid flow. That would either be like the Euler or Navier Stokes equations. With Chuck Moore's digital electronic simulator, his governing equations talk in voltage, current, and charge. Okay. For a dynamic simulation like this of an object in space, the governing equations are called the rigid body equations of motion. Okay, I'm going to show them to you. Don't panic. Don't turn off your computers. Don't walk out. Just all you need to understand is what I'm going to show you. Okay, and the reason I'm going to show you this is this drives the software. Okay, so this is the first of the equations. If those of you who have a little bit of math under your belts will recognize that this is an ordinary differential equation. Remember how I said that the velocity of the vehicle along its x-axis through space is called U? Well, here's U. So what this equation tells us is the rate of change of u with time, rate of change of velocity. In other words, it's telling us the acceleration of the vehicle down its own x-axis, okay? And if you look over here, this is the sum of the forces along the vehicle's x-axis, and this is the mass of the vehicle. So A equals F over M. Sound familiar? That's Newton's second law, okay? Ignore what's to the right of that. That doesn't matter, okay? And you may say, well, okay, there's u, so there are probably two other equations, and there are. There's the equation that shows the acceleration laterally along the v-axis. So this is the acceleration left and right, and then this is the acceleration vertically along the z-axis. So these equations tell us the linear accelerations of the vehicle. And you would think, okay, what about those angular velocities? Well, there are equations for those too. These look worse, but P here is the roll rate, remember? So what this equation is telling us is the roll acceleration, the angular acceleration about the x-axis of the vehicle. And just like above, here's the sum of the torques about that axis, and here's the moment of inertia about that axis. Okay, alpha equals torque over moment of inertia. That's Newton's second law for angular motion. The rest of this, just ignore. Okay, but you get the idea here. And of course, there are two other equations that go with this that show the pitch rate, the pitch acceleration, and the yaw acceleration. Okay, so those are the first 6 equations. There are a few more yet. There are equations that tell us the orientation rate of the vehicle. Phi is the roll angle of the vehicle. Theta is the pitch angle. And psi is the heading angle. So each of these 3 equations are showing us the rate of change of those angles. But look what goes into them. Here's P, Q, and R. And even worse, here's theta. Down here we have the rate of change of theta. So, and if you remember the previous screen, we had the rate of change of P, Q, and R. So all of a sudden what we realize is we can't solve these equations unless we integrate some of them in time. So an integrator becomes one of the central pieces of software in a dynamic simulation. Okay, let me show you the last 3 equations here. And these equations show the velocity across, essentially the velocity north and south, that's what x is. The velocity east and west, whoops, I keep doing that, sorry. East and west, that's what y is. And then the velocity vertically, which is z, okay? So with these 12 equations, you can now simulate the movement, the motion of a body in space, okay? And what drives these equations, I'm going to go backwards for a second here. What drives these equations is the sum of the forces and the sum of the torques on a vehicle. And those are caused by aerodynamics, ground reaction, whatever, okay? So let's see, where am I going after this? Stand by. Okay, yeah, so given that, let me show you some code. Okay, let's get out of this. And I'm going to bring this over. Okay, you guys should see my editor now. Okay, this is the simulation itself. Okay, this is the main load file. I'll show you a little bit about how I write forth. Every file that I write has a header on it. Okay, in some cases, that header will actually contain references to the most important, the top level words in that file, and show you how to use them. So you don't have to actually go down into the file. You just look at the header. You might see 1 or 2 of those as I work through this. There's a set of library routines that I load, and one of those is the integrator. Okay, we'll get back to that in a minute. Down here, these are the actual main application files for the HL-20's simulation. You can see there aren't that many of them. Okay, these are the Forth files. This set up here is a set of Forth files. This set down here is a set of Forth files. This middle set here is a set of, this is the aerodynamic database for the vehicle. It's huge. The simulation actually has to do a 4-dimensional interpolation every time step to figure out what the aerodynamic forces are on the vehicle. That's actually 16 interpolations. So there's a lot of processing going on here every time step. Literally, the size and complexity of the aerodynamic database kind of drives the speed of any flight simulation. Okay, now, one of the other things that I can do here, remember I said that I wanted to develop rendezvous and proximity operations controls for HL-20 while it's operating close to the International Space Station. So I also have to simulate ISS. And this is the ISS model down here. That's all of it. That's all there is to it. What is that? 5 files. The reason it's so much simpler is because there are no aerodynamics on the ISS. It's out of the atmosphere. So I don't have to do any, I don't have to calculate any of the aerodynamic forces or moments. I don't have an aerodynamic database. Makes it much simpler. Okay. So let me show you this. I was just showing you the equations of motion. And big surprise, there's a file called equations of motion. Okay. So let me move this out of the way if I can. Give me a moment here. Yeah, good. Okay. This is the equations of motion file. Let me go to the top of it for you here. Okay. And what you're seeing here is the embodiment of those equations in Forth code. Remember I was talking about, we saw the first differential equation was the u dt. That's right here, u rate. Look how little there is to it. Here's the dv dt equation and the dw dt equation. Here are the angular accelerations, the p rate, q rate, and r rate equations. If you see, they're more complex, but if you look at them line by line, you can see what they're doing. Okay, one of the things that I strive for whenever I write any code actually is to try to make the code tell you what it's doing. Okay, so you'll see that every word name I have is as descriptive as I can come up with it without being verbose. Sometimes I go over the verbose line. When Rick Van Norman and I began working together, he was kind of used to writing some cryptic code. He wrote an interpolator for me, in fact, and he showed me the code, and I said, this works great, I understand it, but it's not talking to me, Rick. And he said, what do you mean? He said, I need each of these words to tell me what it's doing. I don't want to have to spend the time to reverse engineer them. I want them to say to me, here's what I do. And eventually he got it. And he started writing some beautiful code for me. But this is not common out there in code land, regardless of the language you use. In Forth, it's the easiest, so far it's the easiest language I've found that allows you to do this. Okay, so continuing down, here are the other equations yet. You remember there was a psi, that's the heading, theta is the pitch angle, and phi is the roll angle. So they're there also. Ignore the quaternions, you don't even want to know about quaternions. And then again down here, remember we saw the north velocity, east velocity, and down velocity. So it's all right here. You see the equations encapsulated in Forth. Okay. So now the trick is, remember that these are all giving us rates, and what we're actually interested in is not the rates, but their state values. So we're not interested in u acceleration, we're interested in u. We're not interested in x velocity, we're interested in x. So we have to integrate these things. And over the years, there are a few things that I liked about Simulink that I stole. One of them is that, and I don't know how many of you are familiar with Simulink, it's a graphical programming language where you can take a block, put it on the screen, another block, and you can connect them with a line that says this value is being carried. They call that a signal, okay? And the neat thing about Simulink is if you have a signal, you can put an integrator block there, connect the signal in, And let's say that's acceleration coming in, and out the other side comes velocity. That's kind of nice. I said, I want something like that in my simulations. So I wrote an integrator that is extensible. Okay, let me go to this file, globals file. And this will show you how the integrator works. You remember we were talking about with the equations, du dt, dv dt, dw dt. Well, you can see those right here. They're rates. And their states are u, v, and w. So what I've written is an integrator that allows me to define a state followed by its associated rate. Okay, so I can say state u, its rate is du dt. And the integrator will automatically integrate this rate to this state. Okay, all I have to do is update the value of this rate every time step. So I've got words, and I'll show them to you, that update each of these rate values each time step. And then the integrator does the job of following all these and doing the integrations from right to left. These are all held in a linked list. So I can create as many of these as I want. Okay. In fact, let me load up a little bit here. Give me a second. Okay. What I just brought up is a Swift-Forth window. I'm doing all this work in Swift-Forth. And let me load the simulation for you. Okay, that's it. It's loaded. As you all know, that's how fast Forth compiles. Let me clear this so we can see things. Remember I said that each of these states and rates are held in a linked list. Well, I can show myself that list. Display state rates. Oh, okay, and I forgot, I'm actually loading the ISS portion of this as well. But if you look at the bottom here, here's U, which I defined right here. And here's the UDT associated with it, which I've defined right here. And going up the list, you'll see every value over here in the list. And then in another file, I'm doing the same thing for the ISS values. So they're getting included here too. Okay. So this is the entire list of states and rates that the integrator has been registered. Okay. Now the only thing that's left, let me explain a little about the integrator. The integrator is an RK4 integrator. It's a 4-stage integrator. Four calculations are done for each time step. I'm going to bring it up and show it to you. Where am I? Okay, yeah, this is it. Right here, this is the top level integrator word, time step. You call that, the integrator goes out and does the integrations on those values that I just showed you. It does it in 4 stages. So here's the first stage, second stage, third stage, and fourth stage. After those calculations are done, you've advanced the system forward 1 time step. Okay, and that time step is usually on the order of like 50 milliseconds for an airplane. But look what's included here. So you see execute rates. Every time it does its work, those rate values need to be filled in. So there's another linked list where I can register a rate setter with the integrator. So let me clear this. And there they are. Those are the rate setters in the system. These words set those rates every time they're called. So you can see set ISS body rates and set body rates. So set body rates is for the HL-20. Okay. Let me show you those, because that's right at the bottom of the equations of motion here. So remember that each of these equations of motions words is calculating a rate. So down here, this is where I actually call those words. Here's new rate. And I'm setting that integrator value. So the integrator is calling set body rates, and then it's doing the integration. Let me go back to it. Execute rates. And then it's doing the integration, advanced states to something, right? And then after that, it's doing something called execute auxiliaries. When it comes to an aircraft, there are auxiliary equations that have to be calculated afterwards, after an integration step, because they calculate the aerodynamic values, the angle of attack, the angle of side slip, and stuff like that. And again, there's a linked list of those. There they are. So you can see, set the altitude, set the side slip and angle of attack rates. A whole bunch of stuff happens here. Again, this is all aerodynamic calculations. So those have to be executed every integration stage as well. So there's a registry of those as well. And let me go back to the equations of motion. Here's the set body rates word. The way it gets registered with the integrator is right here. Tick, set body rates, sets rates. Okay, as simple as that. For the auxiliary equations, let me show you a few of those quick. Here's how they get registered. Oh, sorry, that's an initializer. Let me come back to that. Do I have an is auxiliary? There's a similar structure where I can say tick word is auxiliary, or what I'm doing here is after I define a word, I can say plus auxiliary, and that assigns it to the auxiliary list. Okay, so there are these linked lists with assigning words that allow me to set up the integrator and connect it to everything I want in the simulation. The beauty of it is that I can set up a whole dynamic system here for one thing, and later on, I can just add another thing if I want. For instance, in this case, I've added ISS in a later file. When we wrote the simulation for the Dream Chaser, I had to simulate a whole bunch of internal stuff there, engines, thrusters. They had their own dynamic set of values. Even the propellant tanks and their propellant levels, same thing. So this gives me the same capability that you would have if you were using Simulant. Okay, except I think it's clearer. So that's how. This is basically how the simulation runs. Okay, you got your equations of motion. You need to integrate them. Those integrated values feed other equations, you integrate those, and you come out finally with the values that you're interested in. And it's all driven by the integrator here, by one single top-level word, advance. So you give advance the amount of time you want the system to be moved forward into the future, call advance, and it integrates that distance into the future. So if I want to just send the system 1 second ahead, it's 1.0 advance, and that does all the work. Okay, so let me give you a little demo, I guess, since everything's loaded up. Let me reload first. Yeah, let's do this. Let's do this. Okay. The numbers you see counting up in the left-hand corner there, that's the elapsed flight time in minutes. So right now we're at 17 minutes, have just gone by. What I've done here is I've started both HL-20 and the International Space Station at the 0 degree latitude, 0 degree longitude point on Earth at an altitude of 214 nautical miles. Okay, it's 400 some kilometers. I started them each at about 17,000 miles per hour. The ISS, I started with an orbital inclination of 51.65 degrees. So that you can see the two vehicles operating, I started HL-20 at an orbital inclination of 50 degrees. So a little less steep. Right now, as we're watching, the system's running, it's advancing ahead in time, and it's saving out a KML file key, oh my God, keyhole markup language, which is a markup language that Google Earth can take as an input file. Okay, it's being saved out as we're talking here. And what we're going to do is I'm going to run the simulation up for 200 minutes. That's 3 hours and 20 minutes of flight. And we'll see what happens. We'll look at the result when we get there. As I showed you before, ISS doesn't have any aerodynamic values associated with it. There are no aerodynamic forces or moments on it. But even in outer space, there are small aerodynamic forces and moments on HL-20. You won't actually see them with, when this comes up and displays, but there's a great deal more calculation being done on HL-20 than there is on ISS. So now it's going to open Google Earth, and there's our result. So, like I said, I'm starting both vehicles at the 0 degrees latitude, 0 degrees longitude point. ISS is the yellow track here at 51.65 degrees. HL-20 is the orange track at 50 degrees. And you can see they're orbiting Earth at 214 miles at a speed of about 17,000 miles per hour. The orbits themselves are actually stationary in space. So if you picture just two circles that happen to intersect at this point, they're just stationary in space, but the Earth is rotating beneath them. So each time they come around on a new orbit, they have shifted to the west. The Earth is rotating west to east. So they look like they're shifting to the west. They are. So this is what happens. This is how the simulation can simulate something that's outside of the atmosphere. Okay. Let me see, what can I go to next? Let me show you something else. Okay, right. The whole reason that I wanted to do this is because I wanted to create a control system for HL-20. Okay, so let me give you a demo of that quick here. Okay, set up for that. Now, I'm going to show you some of the navigation control algorithms for HL-20. It's got to do some kind of high level stuff. There's actually a set of lower level control algorithms here. Again, you can see my header here, but here are some of the things that I'm controlling. Here's heading control, where I can give it a heading command, and this control word will take and point the nose in that direction. Track angle, in other words, the path that it's flying across the Earth's surface is another one, the course. So I can give it a course value and tell it fly course, and this will steer until the course itself is on that bearing. Okay, so I can say fly 45 degrees, and it'll turn the airplane until it's flying on a line that's 45 degrees, regardless of wind. Okay, orbiting a point is important for the HL-20 because that's one of the ways that it can actually approach a landing. I think I got that wired up right now. We'll check that. And then finally, flying a track is very important because you want to be able to put waypoints on the Earth and say, fly from this point to this point to this point. Okay, so that's flying tracks. So you can get an idea of the way I code here. Most of my words are pretty small. If they get big, I realize that I've made a mistake in how I'm embodying the code or in my solution. Maybe I haven't come up with a simple solution. Oh, and here's another thing that I do. Every file I write always has a testing section at the bottom. If it's only a few words to test the whole thing, I just put them here. If it's more than a few words and the tests themselves could occupy their own file, then I put them in their own file. And if you set this to true, like it is now, it'll actually load that file. Okay, and let me show you then the file itself. Yeah, here we go. And then at the end of the test file, I just switched. Oh, no, I didn't. I don't do it here. Sorry. After the test file is loaded, you can see I post a message saying I stopped compilation here, and then I call an abort. So the compilation stops after I've loaded those test words. Okay, so that's what I'm doing here. I've got the test words for these navigation control algorithms loading. So let me see if that'll all load up. Good. Yeah, so you can see stop at the bottom of HL-20 navigation control. Okay. So now what do I have active over here? Yep. Okay. So what I'm going to show you now is the control system controlling an orbit. Now this is an orbit about a point. Okay, not an orbit about the planet. Again, I think I'm starting the vehicle out at the 0 degree latitude, 0 degree longitude point. I have it fly forward a little bit, and then I set up the orbit. I tell you, I tell the system, here's the center point of the orbit in latitude and longitude, and here is the radius of the orbit. I think it's in feet. Okay. Now this is a relatively short simulation. I think this goes for like 13 or 14 seconds. 13 or 14 minutes, sorry. And you can see the minutes counting up on the upper left of the screen here. And there we go. So you can see the aircraft is entering into a right clockwise orbit. I can change that. If I wanted to run counterclockwise, I can do that as well. And again, the control algorithms are set up so that it will be in the correct position here, even with wind. There's a little bit of error involved. You'll see that it gets pushed off a few feet from the actual orbit, but it still does a pretty good job of tracking it. Okay, so that's one high-level control algorithm. Let me show you flying a track now. Oops, I have to turn this one off. Oh, here's another thing. This goes back to the integrator. You see how I'm saying tick orbit is synchronous? I want this word orbit to be run every time step. This is what's actually controlling the vehicle. So there's another registry that goes with the integrator, and those are synchronous words. And I can see what those are as well. So you can see here's orbit, this one that I'm declaring right here. And you can see I'm also running a roll angle controller. Beta is side slip, so side slip controller, a wind model, and then other words here that are being run once a time step as opposed to once an integration stage. Okay, so okay, I'm going to do this. Now I'm going to set up the track test to run synchronously by uncommenting this. And just to show you, now you can see this is the track test. It's called Fly Approach. So that's loaded and is going to run synchronously now. So again, this is a relatively short test. I think, again, this runs for like 14 minutes, which is to us a little less than 14 seconds. Again, this is another benefit of Forth. It runs this kind of, for a scientific language, it is the most powerful one I've ever worked with. It runs things the fastest of any language I've ever worked with. You see this one occurs in Florida. And this is the flight path of the vehicle. I'm actually starting it out in the wrong direction here. I have it flying directly north. But the first segment here, flight segment, actually runs along this line, east to west. So you can see it's making a very large correction here and getting itself back on this track. And then flying to, there's a waypoint right here. And then a waypoint here, one here, and then two down here, actually. And the interesting thing is, if I zoom in here, you'll see that this is the space shuttle landing runway. And we're doing a pretty nice job of tracking the center line of that runway. So the track flying algorithms are working pretty well. The other thing I can show you here is the other thing that's operating here is the altitude control algorithm. Let me see if I can do this. Here we go. And this will show you how I'm commanding the vehicle to descend once it enters the approach path here, the pattern. Now it's not quite actually landing on the runway because I don't have a landing gear model involved yet, but it is flying over that runway at 10 feet of altitude. So when it comes time to land, I'll be able to make it land. I think that's probably going to be it for now. Let's leave like 10 minutes if you guys happen to have any questions. Feel free to ask.
Richard, impressive. Thank you so much.
Thank you.
There are people in the chat making questions. Hi, who is the next one with some questions to Richard?
Stop sharing my screen. There we go.
So I like how we had a conversation in the fourth 2020 group just recently about avoiding local variables, and one of the circumstances where people were saying, hey, quadratic equations and complex calculations, you need local variables lots of times, and your code seems to dismiss that belief fairly well. What are your opinions about that?
The only time I have ever needed to use locals is when I'm writing words to work with Windows, directly with Windows, right? Like, working with a Windows GUI or something like that. A lot of the Windows calls take so many input values. And in that case, I use locals to keep it clear. But in my experience, if you work through your problem correctly, come up with a simple solution, and then think about how to properly decompose and embody that in code. I don't typically find any need for locals whatsoever, even in code that's as complex as this.
Yeah, that's been my experience as well, but I have not done anything nearly as mathematically complex as this. So that's just like, if you could do it this way, then that decision is determined. This is like really great. I love how you kind of create a domain specific language and then solve the problem with your domain specific language, right? That's all proper forth. That's the way it goes.
That's fourth, baby, right? Yeah.
Yeah.
One thing I'd like to say, I've done the same work in C and other languages, Simulink and MATLAB, of course. Fourth is always the fastest for two reasons. The first is, if you think about it, when you're programming in C and you call a subroutine in C, what's actually happening at the machine code level is that when it's time to do the subroutine jump, all of the values in the registers in the processor are stacked. It's called a context state. Okay, so boom, 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 boom. You still haven't gotten to the subroutine. You're still storing stuff on the stack. Then it runs to the subroutine, executes. When the subroutine's done, the return pulls all that stuff on the stack and puts it back into the processor's registers. So in C and almost every other conventionally compiled language, the more you decompose your code, the slower it runs. Okay.
Yes.
Additionally, in fourth, then it doesn't do that because we have we're working on a threaded execution scheme. So our move to a subroutine and back is almost instantaneous. There's very little overhead there, But in addition, in fourth, especially like with Swift fourth here, when I'm doing floating point calculations, I'm putting values directly on the 8-element stack of the floating point coprocessor. Okay, and I'm operating on them right there. In a conventional language like C or the others, they have a floating point stack. So your value goes onto that stack, the next value goes onto that stack, and then plus needs to be run. They move from the stack over to the stack of the floating point coprocessor. They're operated on, and the results move back to the top of the software floating point stack. So Forth is dramatically faster as a scientific programming language. Just wanted to point that out.
Cool. Have you ever been in a situation where you've needed to use something like a GPU or special instructions available on the processor?
Yeah, I've used GPUs for the CFD work. It's actually not that hard.
Right.
I don't remember details anymore, but when I was in grad school, that's one of the things that we did was use GPUs for some of our CFD processing. And it's really not that hard. You just need to make sure that your assembler has those primitives in it so that you can make that thing operate. That's really all there is to it.
Did you use Vulkan or something like that?
No, I was actually using VXF or VFX.
Okay.
Under Linux.
Okay. We have Atli also with some questions.
No, there no questions, just a comment. This is the most beautiful thing I've seen in years. That's all I wanted to say. Thank you.
Thank you. That's very kind of you. Thanks.
Me too. +1 here.
Thank you.
I am waiting. We all, not me alone. We are all waiting for Richard's presentation. I chat with Richard from times to times about his excellent input about space application, because I love airplanes. I love to design airplanes in small scale, but I have also friends who build airplanes and customers. My company has customers in the aerospace industry in Brazil, and it's really an amazing team. And I would like to invite Richard again for our next meetings whenever he wants to come and talk about this fantastic. We have seen in a live demonstration of the pole of Chuck Moore. And I think you have more to show us, Richard, in that.
I'd be happy to. I'll be in the next meeting. I'll come up with something else to show you.
Okay, fantastic. Should anyone with questions to Richard?
Yeah, one other thing, Richard, I was sort of interested. I mean, your code is beautiful, right? And there's a true craftsman in writing code, I think. And I mean, it's a bit like I don't know whether Pascal said it or whether it was Mark Twain. You know, I would have written a shorter letter, but I didn't have time. And I think Voltaire. You know, I mean, yeah, probably Voltaire originally. You're right. So I mean, the elegant code is always great because, you know, you can see it and you can feel the way it flows, and there's a lot of advantages to it. But I was also interested in your debugging words. So you've got various things to show you, and I wonder whether you could just spend 30 seconds talking about that, because that's something that appears to me, especially with Forth, it's got this. In C, you can build that stuff, but it's extra effort that maybe is lighter weight in Forth. And this sort of, the gap between the sort of human and the machine needs to be as close as possible. So I wonder whether you got anything about these words and how you think about those.
Oh, what you said is extremely important. This is another thing that separates Forth from the other languages, right? We can incrementally test our code without any overhead. Write a word, test the word, right? But this also requires that you write small enough words that you have a limited set of inputs and you know what the outputs will be, right? So you test the word with inputs that you think it will see, and then you test it with some that you know should break it, and you make sure that it breaks it so that you fully understand what the word does, right? So that's how I write my code. Everything you see here was incrementally tested, you know, one word at a time. Other things, like I was displaying the list of different words in the registries. Those are things that you need to put in so that you can also get that transparency into the code, right? That's a big thing. When you write something like, I complain a lot about MATLAB and Simulink because they should be complained about, but what you see there, whenever anybody writes embedded code with one of those systems, they use what's called the autocoder. The autocoder takes the diagrams and transcodes them into C. And then you can run a C compiler on that and get executable code. But look how distant you are from the code. You know, you lose the transparency. And I think this is also one of the reasons that Python is so popular right now, because you can also run Python interactively like this, right? Makes it easier to learn. And then I think people have an innate understanding of, hey, this works well, you know, compared to, say, like writing a bunch of C and then having to write a test word at the bottom and linking that into main, and then just running one run of it and saying, did that work or not? You know, there's no interaction. You can't get in there and actually feel what the code is doing. With Enforth, you can. Yeah. So that's when I first started working with it, that was one of the revelations that just grabbed me, was the fact that I can actually see everything that's happening in here as I type. You know, so I hope I answered your question.
No, agreed. Everything you've said. You know, I mean, I think this is the problem that, I mean, if you've got a well-defined problem space, then sometimes, you know, you can have a very strongly typed language that you need to do a lot of boilerplate. But you need a well-defined problem. And it turns out that most problems aren't well-defined. So you've got exploratory work to do. And Forth is one of the languages. I mean, the other places, Python was another one, although I still find myself either embedded or what's it called? It's hard with Python. There's still an extra step to get the interpreter and to incrementally test it. It's tricky with Python. I mean, I like Python a lot, right? Don't get me wrong, but it isn't as close as Forth. The only other place I've potentially seen it really is some of the old 8-bit basics had, you know, but by their inherent nature, there was sort of an interactive nature, which was similar to Forth in a lot of ways. And it's, I mean, obviously, as for instance, Steve Vickers on the in the UK, Steve Vickers with the Sinclair Spectrum line was the same guy that did Jupyter, and he was influenced by Forth. You could tell that in the Sinclair Spectrum ROM, actually, with things like the floating point libraries was obviously inspired by Forth. So it's sort of, I don't know how to explain this to non-Forthers, right? Because they all think I'm crazy, but I'm like, you need to get closer to the machine, not further away.
Yeah.
You know?
Yeah. And,
anyway,
and
thank you.
The conventional wisdom is to put a new layer on top to try to simplify what's below.
Yeah,
right?
yeah. But that's great, apart from when the abstractions break or when you don't know what's happening inside the box, right? You know?
Right. And Rob, you brought up something else that's a very important thing to me that I try to teach people. And that is that when you're working a problem, you need to set yourself up with a sandbox, right? Because what you need to do is you need to play with that problem. You need to start developing an intuition about how the problem works and start developing ideas about how you might solve it, right? And that happens from getting into it, playing with it in the sandbox. For the stiffs, the business stiffs, I call this exploring the solution space. Okay. But this is what I don't see happening in a lot of cases. People sit down and just start typing. And they haven't found a simple solution. They've got a complex solution in their head. And now they take that complex solution and embody it in complex code. But you need to work in that sandbox until you find the simplest solution you can come up with. And then you need to develop another sandbox so that you can play with how you're going to decompose that into code that can be understood, not reverse engineered, but understood straight, and is highly supportable. Now you got a solution. Now you got something to work with. So thanks for bringing that up.
Can I ask one more question? It's kind of related to this. So Margaret Hamilton, after she finished the Apollo program, she did this big study on the types of errors that are encountered in software. And from my readings of her works and everything, so she actually came up with a proposal for a provably correct system, which she did not describe it as such, but it really is a stack-based system. But it never came out to anything. But I'm curious, what are the common bugs that you run into? And have you ever found yourself wishing, like, maybe if I had a stronger type system that would prevent that category of bugs, or do you find that the way you decompose your words, you just don't need a type system at all?
Yeah, who wrote Pascal?
Nicholas Worth.
Yeah, Worth. Worth was a huge proponent of strongly typed systems, right? And I don't know how many of you have worked with Simulink, but Simulink is the most strongly typed programming language that I think has ever been developed. Literally, if you set up a signal, and on that signal, you put a label that says, this is lift, right? You can't connect that lift to any other signal unless it goes through an operator. That's how strongly typed it is. And yet, I have seen so much failed Simulink code, you wouldn't believe it. And I've had to watch as other programmers prior to me have gamed the system because they've come up against something that they wanted to do that the typing kept them from doing, right? So like literally in one system, there's a signal coming along and the guy couldn't connect it. He couldn't do what he wanted with it. So he put a gain in there, a gain of 1. And that gain allowed him to change the type of signal from the left to the right. And now he could work with it. So I come along and look at that gain and I say, what's this gain do? It's 1. Should this be here? Did the previous author intend for this to be here? Did they somehow screw up and reset it back to 1? I mean, who uses a gain of 1, right? You know, so all of a sudden you've introduced this ambiguity into the code that makes it unsupportable. You know, in my code, you know, I've had to work with other people, introduce other people to Forth. And one of the things that they always throw their arms up about, there's no typing, there's no typing. I've never found that to be a problem. You know,
So what category of errors are you actually encountering when you're building your style of code?
The only time I find like a type error is where I write minus instead of F minus or something like that, right? You know, with floating, I don't know how many of you have used floating point and Forth, but there's a separate set of operators. You know, you got plus, minus, and all that for the integers. There's F plus, F minus, and such for the floating points. So every once in a while, I'll make a typing error like that. And of course, you try to run the code and it crashes, right? So then you go back and start looking and say, oh, okay, I missed my F, you know. But aside of that, I have never experienced any kind of a type error in Forth. I think the thing is that if you do your decomposition right, fine enough, right? Then when you're working in words, you know what needs to go where. Even if you're mixing integer math and floating point math, it doesn't seem to really, it doesn't seem to get mixed up in my case, in my opinion, you know, my experience. So I haven't found typing to be a big deal.
When you were at Aston, did you recall running into a guy named Michael Mealing? He was like this. Yeah. So he's a friend of mine from Atlanta. We were all in private space and the Libertarian Party together.
Okay, cool.
Yeah. I wish I could do private space programming. I'm so jealous of you.
I'll tell you what, it has not been easy to do the work that I've done. You know, there's a lot of opposition to doing things the right way out there. And a lot of it comes from other engineers who don't have enough experience. And the rest of it comes from management who has no experience. And I come along and tell them, literally, when I was working at Stratolaunch, they had a flight simulator that had so many problems in it that the pilots were frustrated, the engineers were frustrated. And I looked at the code. I literally found a block of code that I couldn't understand. I couldn't tell what it did. It was literally like 20 blocks with lines in them. And I looked at this and realized, this is the most amazing thing I've ever seen. I actually cut it out and framed it and put it up in my cubicle and said that this should be the entry, the US's entry into the National Obfuscated Code Contest for the year. And I used to hand that framed picture to people and say, here, tell me what this does and tell me what comes out of this output. Nobody ever got it right. I'm the only ever person that figured out what the output was. 1. A constant 1 came out of this set of 10 blocks. But literally, I never figured out, what does this do? What's it supposed to represent? You know? And so this is the kind of code they were dealing with. They had people the customers of the system who hated it. And I come along to management and tell them, guys, this has to be redone. And we're not going to redo it in MATLAB and Simulink because this is what you end up with. And they say, oh, no, this is fine. So this has kind of been my life, is trying to convince people to do things the right way when they think they know more than I do about it. It's not easy.
Awesome
Fantastic, fantastic. Now we